So today's topic is about transistor scaling and semiconductor fabrication techniques. And I'm actually really glad to see this many participants interested in this kind of a topic in Sri Lanka. We have to make sure that this kind of technology actually gets into Sri Lanka and that the knowledge is actually shared among us. So I am also thinking that a lot of participants today are from diverse backgrounds. And this topic actually needs spans over multiple fields when it comes to transistor scaling and semiconductor fabrication techniques. It can use some sort of chemistry, and then sometimes it needs engineering. It spans over engineering physics and also semiconductor device physics. So I was trying to balance my talk between the topic itself and also the subject areas that we have to touch. So I also have to balance and bring certain questions and certain subjects, touch certain subjects that are actually relevant to the CHIPS challenge as well. So I may actually go over some fundamentals, and then I will go over some advanced materials as well. So bear with me if you have studied the fundamentals before in some of your classes or in the university, but I think it's essential for this topic and also for the CHIPS challenge. So let me go over the outline of my talk. I will go over the history of the transistors, and then I will introduce the Moore's law, and then talk about scaling transistors. Then I will go over the p-n junction diodes. Then move on to MOSFET transistor and the theory. Then I will discuss why we are scaling the transistors and why we need advanced transistor architectures. And then finally, I will go over the semiconductor fabrication techniques. So, before we start, I want to ask you, what do you think is the greatest invention in the 20th century, right? So, I believe it's the transistor, right? Because the transistors gave rise to logic gates and digital circuits. They also made the integrated circuits, the ICs, possible. And because of the ICs, now we have the computers, the internet, and also the smartphones, right? So because of the transistors, now we went over the information age in 1980s, and then the digital age in 1990s and in 2000. And now we also have the uh, artificial intelligence, the AI. It all started with the transistor, right? Uh, Back in 1946, we had the very first computer. It's called the ENIAC. The ENIAC stands for Electronic and Numerical Integrator and Computer, and it was built during World War II using vacuum tubes. Now, vacuum tubes are bulky tools, right? Vacuum tubes. This is a vacuum tube. As you can see, it's actually pretty big. And when you build a transistor using vacuum tubes, sometimes these vacuum tubes just get burnt out, and then you don't know where that broken vacuum tube is. So it's very cumbersome to troubleshoot. It's very difficult to actually maintain such a computer. And also I have to add that these computers were huge. They were the size of like a huge hall or a room. You can see like this one person operating on this so-called computer, and this whole room is occupied by the computer, right? So the first transistor was invented in 1947. It was invented by Bardeen, Britton, and Shockley at Bell Labs in 1947. And then soon afterwards, the integrated circuit came into being in 1958 by Jack Kilby and also by Robert Noyce, right? So the integrated circuit, the IC, means that you have integrated the transistor, the resistor, the capacitors, and certain other elements on the same substrate, as you can see here, right? So these three gentlemen, they went on to win the Nobel Prize, and again, these two gentlemen, Jack Kilby and also Robert Noyce, also won the Nobel Prize for the invention of the integrated circuit. Now, ever since then, we have been making integrated circuits with a very large numbers of transistors, right? So initially it was around 1,000 transistors or 500 transistors, but then in 1960s, the Intel co-founder Gordon Moore observed that the number of transistors in a semiconductor chip doubles roughly every 2 years or so, right? So when you double the number of transistors in a chip, the functionality increases by many folds, and the cost of fabricating a chip, though the cost per transistor goes down by half every 2 years, right? Uh, Now, this was just an observation. It's called Moore's law, not a law, but the semiconductor companies in Silicon Valley and elsewhere took this to heart so much they have been trying to keep up this trend, right? And that gave rise to the miniaturization of the transistor and also scaling of the transistor, right? So the advantage of scaling the transistor this way is that when you scale it and as it becomes smaller and smaller, it has increased computing power because you are doubling the number of transistors every 2 years, so you have more functionality in the chip, and then performance also goes up because the gate delay is much less, right? The RC delay is less, and then it becomes more energy efficient. And also, more than anything, the economies of scale comes into effect, and the cost of the microchip goes down, or the cost per transistor actually goes down, right? So what actually happens is you can see the microprocessor transistor count over here on the right hand side of the slide. In 1970s it was around 2000, and then in 1990s it was more than 1 million transistors in a chip, and then we were using desktops, and then in 2010 we were having laptops, and we were having more than 1 into 10 to the 9, so billion transistors in a single chip, right? Then by 2020 we have more than 10 billion transistors. Now it's actually close to 100 billion transistors in one chip, right? So as the number of transistor is getting larger and larger, as it is increasing, the size of the transistor also has been going down. So we call this scaling or the miniaturization of the transistor. So initially it was in the micrometer range, the size of the transistor, and now it's in hundreds of nanometers, and now it has reached close to 10 nanometers and below one transistor, right? So you can imagine if you are trying to manufacture something that's close to uh, uh, 10 nanometers in size, right? You need tremendous amount of thinking, critical thinking, and analysis behind it, right? So for the last 50 years, we have had a lot of innovation in this field in materials engineering, in semiconductor process integration, in solid state devices, and also in electronic engineering. I don't think any other field has evolved this much over the last 50 years. So the best brains have been working in this field to make sure that we can miniaturize the transistor and also design circuits out of these transistors to get the best out of the best functionality for the silicon chips. Uh, did I get stuck? Yes.
No.
Yes. Yeah. So why do we need semiconducting materials for the transistors, and why silicon, right? Uh, so we need semiconducting materials to facilitate the operation of transistors, because in the transistors we are trying to modulate the conductivity by either introducing certain other materials like such as dopants, as we call it, or by applying an electric field, right? Uh, so if you are familiar with certain types of materials and their band diagrams, you know that in conductors, you have ample amount of electrons that are free to move within that material, right? And there is no band gap. The electrons are free to move within the material. And if you look into the insulators, all the electrons are stuck into the atoms, into the lattice, and they are not free to move. And in the conduction band we almost have zero electrons to move around, so that means it's not conducting, so it has a really wide band gap, and the thermal energy is not enough to excite the electrons from the valence band into the conduction band, right? But the semiconducting materials actually have a very reasonable band gap around 1 to 2 electron volts. So the electrons in the valence band can get excited from thermal energy and then move on to the conduction band. So that means there are certain uh, electrons in the conduction band that are free to move around due to thermal energy. And this number of electrons can then be modulated by either applying dopants or by applying an electric field into semiconducting materials, right? So, as you all know, the semiconducting materials could be silicon, germanium or carbon. And right now, we are mainly focused on silicon technology for transistor fabrication, mainly because silicon is the most abundant and the cheapest semiconductor that we can find, right? And also, silicon has a very moderate band gap, around 1.1 electron volts, and silicon is also really good at forming oxides, and that silicon to silicon dioxide interface, once you form the oxide, is also excellent, and it does not have many defects. uh, so I just mentioned that silicon is an abundant material, and where does this silicon come from, right? Silicon actually comes from sand, and sand, like most of the Earth's crust is actually made out of sand, right? I would say about like 30% from what I have heard. So sand, what we actually do is we get sand from particular areas of the world where sand is actually ultra pure, and then we mix it with coal, and then we molten it, we liquefy it, we apply very high temperatures to make sure that it is liquefied, and then the carbon then connects with the oxygen, and it forms carbon monoxide and carbon dioxide, while silicon is extracted, and you can actually extract industrial grade silicon, which is 99.8% pure out of this methodology, right? So what you can actually do is you can do this over and over multiple times, and also get rid of certain other impurities in silicon, and you can then get extremely pure silicon nuggets purified from sand itself. And once you have the silicon nuggets, this is called polysilicon because the silicon has multiple crystalline, silicon has a particular crystalline structure, but then you have uh, uh, these crystals mixed up in certain ways, and it's not one single crystal in these nuggets, right? So you have polysilicon crystalline, as we call it. So what we do is then we again put this into a furnace, and then we put a certain initiating seed silicon crystal with a particular orientation, and then we extract that silicon from the molten silicon, and then the silicon actually kind of solidifies around that initial crystal, and then it forms a single crystal ingot. That's what you have over here. That's cylindrical in shape. So what we do is we actually polish the surfaces, and then we dice it to obtain silicon wafers, right? So silicon wafers, actually, I do have one right over here. They actually do look like this, right? They are very thin. They are about 500 microns in thickness, and it has a very polished surface. And all these crystalline surfaces are actually well defined. We know exactly what kind of a surface we have. It's the 100 plane that we usually use for transistor fabrication. Once we have this very pure silicon in wafers, how do we modulate the silicon conductivity, right? So that's the key question. And so I want to explain the concept of doping before I move on any further. So here we actually introduce certain impurities into silicon. These impurities are nothing other than group 3 or group 5 elements, right? And there's two types of doping. They are called N-type doping and P-type doping. So, for example, if you want to dope a silicon wafer P-type, right, N-type, sorry, then you apply, what you do is you bombard the silicon surface with group 5 atoms like phosphorus or arsenic, right? So this atom would then come into the silicon lattice, right? Usually silicon is connected to 4 other silicon atoms in the crystal, in the lattice. And now we replace one silicon atom with phosphorus, and phosphorus have 5 electrons in its outermost shell. So then 4 electrons are being now shared with other silicon atoms, and 1 electron is free to move, right? So as you can see here, it has 5 electrons, 1 is free to move, and this free electron then can conduct electricity. And depending on the amount of phosphorus that we add into the silicon crystal, then we can modulate the conductivity of the silicon crystal. The same goes for p-type doping of the silicon lattice. In this case, we are introducing group 3 elements such as boron or aluminum into the crystalline lattice, and then what happens is it only has uh, three electrons in its outermost shell. They are being shared. So one bond is lacking here, and that lack of an electron, as you can see over here, is called a hole, right? So what actually happens is this electron can then jump into this hole, and then there is a vacancy here. There is the hole has moved here. Another electron can then jump into this hole. So eventually, what happens is this hole actually moves around, right? So even though it's the electrons that's actually moving, the holes move in a particular direction, right? So that's how we actually modulate the conductivity of the semiconductor by adding impurities. So, just for the sake of this competition, I want to go over some of the theories of the p-n junction diodes, right? So now, when you have a p-type semiconductor and an n-type semiconductor, if we join them, if you join two pieces of semiconductor materials with opposite types of doping, p and n, what you have is a p-n junction that acts as a diode, right? So, what actually happens here? What happens is that the n-type semiconductor has a majority of electrons, right? And the p-type semiconductor has a majority of holes, as I just explained. So the electrons, the majority electrons, start moving because of diffusion. You have a really high concentration of electrons. You put them in one place, they start moving around very slowly due to thermal energy, right? So these electrons then start moving into the p-type semiconductor very slowly due to diffusion, and the holes also start moving from the p-type semiconductor to the n-type semiconductor due to diffusion, because that's the majority carrier in the p-type semiconductor, right? Now when this happens, uh, within the semiconductor, I told you that if it is an n-type semiconductor, what we have are the p-type donors, right? Phosphorus, right? So phosphorus atoms is sitting here, and the crystal is actually neutral because the charge of the electron and the charge of the phosphorus atom, which is positive, are balanced out. And now, if the electrons are moving into the left-hand side, then this phosphorus atom at the interface is exposed, right? So if it is getting exposed, that means we are exposing certain positive charges, and these charges are now fixed to the lattice because phosphorus cannot actually move within from the lattice. It has a fixed position, even though the electrons can move, right? So in the same way, the boron atoms have the negative charge, right? And it has basically now become an ion. So the boron ion is also fixed to the lattice, and once the holes are moving to the right hand side, it's exposing all the negative charges on the left hand side. So what you actually have is then a particular electric field that's going from positive to negative charges, right? So in addition to the electron and hole diffusion, because of this diffusion, now you have exposed the charged atoms. Now you have created a particular electric field, and due to that field, there is another current that emanates from it, and that's the hole drift current and the electron drift current, right? So the electrons are drifting from negative to positive because they are being attracted into the positive side, right? Electron diffusion happens in the opposite direction. In the same way, the holes are diffusing from p to n type, but the holes are drifting from n type to p type, right? Um, so as this keeps on happening, what we call this area the space charge region, and the space charge region keeps expanding as this phenomena is happening, right? And then at a particular point, at thermal equilibrium, this diffusion force and the electric E field force actually balance each other, right? So the space charge region then gives rise to the drift current, the diffusion and drift currents finally get balanced at thermal equilibrium, as we call it, right? So how do you determine the maximum depletion width in this region? We are not applying any kind of an external voltage, and this happens purely because you have a density gradient in electrons and holes, and then that gives rise to an electric field within a particular material, right? So the maximum depletion width is reached when the diffusion current and the drift currents exactly cancel out, right? So this is a dynamic equilibrium where the charges are still moving, but the net current is actually zero. So don't think that nothing is actually moving once it reaches thermal equilibrium. The charges are always moving due to drift and also due to diffusion, but there is no net current. The currents actually balances out, right? So you can also study these things in semiconductor device physics books. The depletion width is formed, right? And then from P to N, there is a particular built-in voltage, right? And this is what acts as the turn on voltage for the diodes. This potential barrier is usually around 0.7 volts. It's a very important parameter in diode operation. Uh, and then now you can use some of the device physics to derive the amount of current that you can get from a diode, and also you can somehow determine the space charge width, the maximum width that you can get based uh, uh, on the donor and acceptor concentrations. So if you start reading this book, I have pointed out that you should be reading chapter 7 and 8 in Semiconductor Physics and Devices. This is a really famous book written by Donald Neiman. You can download it for free from the internet. It's explaining that the diffusion current is given by this equation, right? So this J just means that it's the current per unit area, right? So this diffusion current from electrons, which is N, is given by E, which is the electron charge, times the diffusion coefficient, and dN by dx. dN by dx is the density gradient of the electrons. And you can write a similar equation for the holes as well. And then when it comes to the drift current for the electrons is given by the electron charge into the concentration, the carrier concentration in 1 cubic centimeter of the semiconductor, times the mobility of the electrons times the E field. Right? This E field then depends uh, on the charges that we have on P side to the N side, right? Or whatever the charge or whatever the electric field that we are applying to the semiconductor. And so these diffusion coefficients also have this other fundamental relationship that comes from Albert Einstein. So Einstein just did not work on relativity, right? He also worked on semiconductor physics, and he came up with this relationship where the diffusion coefficient to the mobility of that particular particle is equal to kT over Q, right? Boltzmann constant into the absolute temperature over the charge of the electron. So that's a very fundamental unit that always appears in semiconductor devices. So if you write the equations for the diffusion current for the electrons and also for the drift current for the electrons, balance it out, and then get the total current, hole current, and the electron current, then you actually end up with this ideal diode equation, right? So this thing then depends on the diffusion coefficient of the electrons and the holes, and it also has the carrier concentrations on the p-type semiconductor in thermal equilibrium. That's what this zero means. And then it also depends on certain diffusion lengths. This Ln stands for diffusion length of the electrons on the for the n-type semiconductor and also for the p-type semiconductor. And if we somehow uh, uh, represent this whole thing with Is, the saturation current, then you can write this equation in this form. And I'm pretty sure most of you are actually familiar with this equation. That's the diode equation, right? It's the equation for the ideal diode. Okay, so if we also know the concentration of electrons and holes in on the N and P sides, right? These are the acceptor concentrations that we dope the material with, right? So if we dope the material with, let's say, 1 into 10 to the 16 atoms of phosphorus per cubic square, per cubic centimeter, then you can plug that number here. You can use the same for the acceptor materials, acceptor atoms, and then this is the amount this is the concentration at for an intrinsic semiconductor, and then this is the thermal voltage, and by using this equation then you can get the built-in potential that I actually showed you earlier, right? So you can see that the built-in potential actually increases slowly from one side to another. It builds up given the uh, electric field that spans from the N type to the P type, right? Once you have this built-in voltage, then you can use that into this equation and get the space charge width as well. So I saw some questions when I actually looked over the microelectronics Olympiad exam that I found from 2016, and that's why I actually emphasize these things. You should definitely go over these chapters and study these things before you actually go for the exam. So with that information in mind, we can move on to our next topic, which is the MOSFET transistor and the theory, right? So I will introduce the MOSFET transistor to you. That's the MOSFET actually stands for metal oxide semiconductor field effect transistor. It was invented in 1959, and it soon replaced BJT transistors, which were used in digital electronics. It's a four-terminal device. It has the gate, the source, the drain, and then the bulk, right? So the MOSFET has, so if you take the cross section of a MOSFET, the structure looks like this. What you have is a p-type silicon body if it is an NFET, and then you have source and drain regions that are highly doped. They have n-type doping for source and drain in an NFET, and then you have a particular insulator here on top adjacent to this source and drain that's usually made out of silicon dioxide. Right now it's made out of a whole lot of other oxides and materials, and then you have a gate on top of the silicon dioxide, and that's usually made out of metal, right? So you have the metal gate, and then you have the gate oxide, and then you also have certain metal contacts to the n-type semiconductor areas here, just to make contact and to make sure that you can apply particular voltages here. So this is the basic structure of a long channel MOSFET, right? So here I also want to emphasize again, this upper layer has the metal. The gate is usually made out of metal, and then you have the oxide, and then you have the semiconductor body, right? So that's why we call it the MOS, right? So metal oxide semiconductor part comes from this one, and then also we are trying to control the current from source to drain by applying a particular voltage into this metal gate, right? And then this metal gate has a particular voltage, so the field lines emanating from the gate end up in this channel, in this area at the interface between the silicon dioxide and silicon, right? So that affects the area here, the channel formation, and then that forms a particular uh, conducting channel that is usually modulated or controlled by the gate. So that's why we call it the field effect transistor, right? So MOS comes from this part, metal oxide semiconductor, and field effect transistor, part of that name actually comes from the modulation of the channel. So other key concepts that are actually important for the MOSFET transistor are the gate lengths and also the gate widths. So the length of the transistor is this distance between the source and the drain, and the width of the transistor is the width in the third in the second dimension, right? So when we are talking about scaling in future, what we are doing is we are actually trying to scale down the length of the channel, which is the distance between source and the drain. Oh, and this is also referred to as the node. So when we are talking about the technology node, that somehow represents the gate length between the source and the drain as well. It could be slightly different, but it's very similar to the gate length that we have in a particular transistor. Uh, so there are different types of MOSFETs as well. There could be N-type MOSFETs or P-type MOSFETs, depending on how you actually dope these wells, and also the doping of the substrate. Uh, for the N-type MOSFET, we always dope the source and the drain N-type, and the substrate is P-type. So from now on, we will only focus on N-type MOSFETs going forward, right? And then there are two other types of MOSFETs, that's enhancement type MOSFET and the depletion type MOSFET. But here we will only discuss about the enhancement type MOSFET. So in an enhancement type MOSFET, the transistor is usually off, and to turn it on, you have to apply a particular gate voltage, a minimum gate voltage that's called the threshold voltage. Uh, So let me go over the operating regions of the N-type MOSFET, right? Uh, Here you can first ground the source and the drain, and then apply a small voltage into the gate. So then the field lines emanating from the gate end up in the channel, right? And then they push away the holes, which are the majority carriers in a P-type substrate, and then it attracts the electrons into the surface, and at the same time the electrons can flow from the source and the drain because they have a lot of electrons in this in the source and the drain because they are doped that way, right? And so if this number of electrons is actually quite small, then it won't conduct any electricity, right? There is no channel formation, and that's called the subthreshold uh, region for the transistor, right? In the second phase is when the gate voltage is slightly high enough, it forms a particular conducting channel between the source and the drain, right? So the current between the source and drain will be zero, and once the VGS, we call it, right, gate to source voltage, exceeds this particular value called the threshold voltage, then it can conduct current between source and drain because it then forms a channel, right? So there is an equation for the threshold voltage that actually depends on the doping levels that we have in the semiconductor, the permittivity of the semiconductor, the surface potential, and also it depends on the this gate oxide capacitance, right? So this is basically a capacitor because you have metal here, then we have an oxide here, and then we have another channel that is conducting. So it's like a parallel plate capacitor as you think about it, right? You can think of it as a capacitor, and then this C ox actually stands for the capacitance between the gate and the channel. So that C ox is actually equal to epsilon A over T, right? And the T is the thickness of the silicon dioxide. Okay. Uh, yeah, so the threshold voltage also depends on the flat band voltage and also the Fermi potential, right? The surface potential of the semiconductors. Uh, yeah, so you can see like all the terms here I have explained here. And then you can also see how this threshold voltage changes when we change certain things. For example, if we change the oxide thickness, if we make it thinner, then the capacitance becomes higher. If Cox is higher, then threshold voltage is less, right? And if we do the if we increase the doping level of the substrate, then this Na will increase and the threshold voltage will also increase, right? So you can actually change the threshold voltage by changing certain parameters. So now, uh, while keeping the gate to source voltage, right, we can apply a very small drain voltage, right? So then what happens is this channel then behaves as a particular resistor with a fixed resistance, right? So if it is a fixed resistance, when we keep on increasing the drain voltage, the drain current will also increase, and then it increases linearly, right? So we call this the linear region and the ohmic region. And now if we increase it even further, uh, what actually happens is the drain voltage, once it reaches a saturation voltage, the pinch off happens. Basically, this potential is now redistributed throughout the channel, and then towards the end of the channel actually does not exist. All the electrons are now being sucked into this uh, drain region because the drain has very high voltage, right? So for a fixed gate voltage, if we keep on increasing the drain voltage, it will then somehow saturate the current, and increasing the drain voltage any further would not increase the drain current, right? So that we call as the saturation region. So you first have the cutoff, and then it goes over the linear region, and then the current would saturate. So it's called the saturation region. And this saturation current is given by this equation. It depends on the mobility of the electrons, the oxide capacitance, the W and the L, and the threshold voltage, right? And these two curves, the transfer curve and output curves, are uh, highly used metrics to understand how the transistor actually functions. So here in the cutoff, you have no flow currents, right? So that's called logic 0. And then at high currents, you can use that as logic 1, right? And this is the output curve of the same transistor. You can see the cutoff region, the saturation region, and also the ohmic regions. So once it saturates though, if you increase the gate voltage, again the channel becomes slightly thicker, and then the current will increase. So that's why it actually increases when you keep on increasing the gate voltage. So now we can move on to transistor scaling and advanced transistor architecture. Uh, so why do we actually scale the transistor, right? I will go over this very fast. So as I mentioned, it has increased computing power. You have more transistors in a single chip, right? So the more transistor users you have, the more work you can do with a given microprocessor, right? And the transistors can also work in parallel to have some sort of multi-threading capabilities, right? And also for AI and everything else. And then it also has improved performances because the gate delay will be reduced, and it has higher switching speeds, and the signals also travel shorter distances between the transistors. So the delay is decreased, and the speed will increase. And then furthermore, we have some sort of uh, uh, initially when we were actually scaling the transistors, we were trying to keep a constant field within the gate oxide. So as we scaled the channel length, and we also scaled the voltage, so smaller transistors require less voltage, so that actually reduces the power consumption. That's not true anymore, but this used to happen for a really long time. And then as we make the transistor smaller, the parasitic capacitance also actually reduces. So smaller future sizes gives rise to smaller capacitances, and then it makes the transistor much faster. And then reduced cost, we can fabricate more chips per wafer, right? So the wafer size, I think I just showed you, this is a 3-inch wafer. They moved on to 6-inch wafers, and then also to 10-inch wafers. The wafer size has now become much larger. Now we are using 300 millimeter wafer. So it's 30 centimeters in diameter each wafer, right? So within in one wafer, now you can fabricate a lot more chips. That makes it even cheaper. And as you have more and more transistors, you have more functionality. So basically, this whole thing is driven by economies of scale, right? So the mass production has made it a lot more cheaper, and it also makes sure that more efficient chips actually drive down the manufacturing costs over time. So what are the challenges of scaling the transistors into sub 100 nanometer nodes, right? So as you can see over here, the first challenge is the short channel effect challenge, right? So here we have a transistor where the gate length is about 200 nanometers. It's working fine. You can consider that as a long channel MOSFET, as they call it. So now you make it shorter, you make it 150 nanometers, you make it 100 nanometers, and you make it 80 nanometers. And now you can see that the source and drain regions are getting closer and closer. And the drain, for the functionality, I told you, we also have to apply a particular voltage to the drain and also to the gate. So from the drain onwards, there are certain field lines that come and stop at this channel, right? So these are like fringing fields that are coming from the drain into the channel, to the channel that's close to the oxide. And as we make this channel length smaller, more and more electric fields actually end up in the channel. A higher percentage of these electric fields, or the fringing fields, they end up in the channel. And because of that, what happens is we lose the gate control. The drain voltage starts controlling the channel. And that's called the drain induced barrier lowering. Because you can also explain it using the energy band diagram. It's actually called Dibble, and then the threshold voltage is now being controlled by the drain. So the threshold voltage also decreases as we keep on decreasing this length. So you can see this is the VT. VT comes down for a particular drain voltage. If we increase the drain voltage, it comes down even further, and it's detrimental to the transistor performance. Right? And then the second challenge is the leakage and quantum tunneling. As we keep on scaling the transistor, this gate oxide, becomes thinner and thinner, right? So uh, once you have around 1 nanometer thick gate oxides, the electrons can tunnel right from the channel into the gate, like as if there is nothing in between. So because 1 nanometer is actually around like 10 atoms wide, right? In this direction, in the vertical direction. Uh, so there are certain other phenomena that's happening, such as Giddle, gate-induced drain lowering, and also the punch-through. I won't go into details here, but what actually happens is that we lose the functionality of over the transistor, the gate control, right? Again. Another challenge is the variability. If the transistor is extremely small, around let's say 10 nanometers, uh, initially if we have 100 working electrons in the channel, you lose just one electron. It's just 1% change in the current. And now if you only have 10 electrons in the channel, right? If you lose one, then you have 10% change in the current, right? So from one transistor to another, there is huge variability nowadays. As it gets smaller and smaller, this percentage impact is getting larger and larger, and it's so there is basically statistical variation between the devices. Another one is lithography limitations. We are basically using light uh, to print the transistors on the silicon wafer, right? And now we are meeting the limitations of the wavelength of light, because uh, uh, the light that we are using is around, we are trying to use the smallest wavelength light, because if you look into the resolution, right, the resolution as the uh, light passes through a particular mask, and if it goes through a lens, then you can resolve two things. That resolution on the silicon substrate depends on uh, is based on this equation where it's 0.61 into the lambda, which is the wavelength of light, over n sine omega, right? And n sine omega is the numerical aperture of the lens, right? So if we make this n sine omega larger and larger, right? Then we can make this resolution smaller and smaller, right? And then another thing that we can do is we can make this lambda value smaller, so we can get much better resolution, right? So in optics that we are using, in lithography tools that we are using nowadays, we have really big lenses, and then we also try to push the wavelength, the exposure wavelengths, into the ultraviolet regime. Right now, initially we were using about blue light, and then from blue light we tried to reduce the wavelength into the ultraviolet regime. It went from 193 nanometers to 157, and now you need uh, about 13 nanometers wavelengths to print very small feature sizes that are below 100 nanometers, right? So these litho tools actually cost more than $100 million each, and then only big foundries like Intel or TSMC can afford them. So that's another huge limitation that we have as we keep on scaling down the transistor. The interconnects. The other challenge is the copper interconnect, right? So there are copper interconnects connecting the transistor from one transistor to another, right? So let's say that this is the dielectric and this is copper, right? At the upper part of the chip. Then if this line width is decreasing as the transistors are getting closer and closer, this copper line width also has to decrease. And then as the line width gets decreased, the copper resistance, the line resistance, keeps on skyrocketing, and that leads to huge RC delays and also power losses. The final one is the heat dissipation. Higher transistor density leads to localized heating, and then more transistors you have per unit area, the more heat is generated per area. So heat dissipation is also a huge challenge in today's chips. Okay, so what are the solutions that we have come up with, right? So people have come up with amazing material innovation solutions, and they have also proposed advanced architecture designs that have worked really well in the last 20 or 30 years. The first solution actually came from Intel to get higher current. So what they actually did was within 20, from 90 to 65 nanometer nodes, they introduced stress and strain engineering, For example, in PMOS transistors, if you want to get higher currents, then you can get less delay and then get higher performance. What they actually did was they introduced silicon and germanium into the source and drain. So the silicon germanium lattice is actually slightly larger than the silicon lattice. So once you embed that into silicon, it tries to expand, and when they try to expand from both sides, it compresses the silicon channel. And as you compress the silicon channel in PMOS, the current increases. And for NMOS, they came up with a different technology to add the tensile strain and then increase the current. So by doing so, they were able to boost the carrier mobility and also the drive current once we cross the 100 nanometer node. The second innovation actually came around 45 nanometer node. So again, I'm referring to this node as this can also be thought of as the channel length very closely, right? So you can replace the silicon dioxide, the gate oxide here, with high K dielectrics, right? So if you have a high K dielectric, what you have is you can make it thicker. So if this is thicker, but if the epsilon is larger, then you can have the same capacitance and you can keep the same current. But the advantage is now that this is much thicker, there is less leakage because leakage actually the quantum tunneling depends on the physical thickness of the barrier, right? So if the physical thickness is much larger now, then there is less leakage between the silicon substrate and the gate. But because because this is a high dielectric oxide, you have the same capacitance and you have the same current, right? And then another innovation that happened was at 22 nanometer node. Um since we only had 2D transistors until 22 nanometer node, and then they went on to 3D FinFET structures, right? So that's the change in the architecture, right? So instead of having flat source and drain on the silicon channel, what they did was they actually made a raised source and drain, right? So it's like a fin of a fish. So that's why we call it the FinFET, right? So this is the fin, the source here, the drain here, and the gate metal is now wrapping around the source and drain, right? So you have a small red oxide here. It's not actually red, but in the picture it's red. But then you also have the metal going over the oxide to control, and then this way you get much better gate control. And this structure actually reduces the leakage and improves the performance over the 2D MOSFET. So what else? They introduced extreme ultraviolet lithography at 7 nanometer node. That was just a few years ago, probably around like 4 or 5 years ago. This enables finer patterning with 13.5 nanometer wavelength light, right? Now, if we try to decrease the lambda or the wavelength any further, what you get is X-rays, right? So we are actually stuck with the electromagnetic spectrum. We are pushing the limits in all fronts to make sure that we are miniaturizing the transistor, but we keep on running into certain brick walls. And it's pretty hard to get around these brick walls because these things actually arise from fundamental physics, right? If you have X-rays, the X-rays would travel right through the optics and also through the silicon uh, wafer, and then you cannot expose anything because X-rays can go through materials, right? So that's why we are somewhat stuck here in this regime, and the best we can do is the extreme ultraviolet around, which has a wavelength around 13 nanometers, right? And then finally, the latest technology that we have right now is the gate all-around architecture. This is also called the nano sheets at 3 nanometer node. What they have is the source and drain now, instead of having a fin, uh, it's actually kind of floating in the air from between source and the drain, right? And so if you cut the cross section, you see it this way. You can make them square or you can make them rectangular. But either way, now you have a very thin oxide around this sheets, and then around that you have a gate metal that's wrapping the entire area, right? So it's just amazing to me to see that they make this kind of structures, right? And sorry, this is an example. This is an SCM cross section of a nanosheet FET, right? You can see that they're actually standing over here. I don't even know like how they actually manufacture these things. I also have to read up and understand how they do it. But they actually do it, and it's just amazing what human creativity and innovation can achieve. So these are the latest material and architecture innovations that's done by just Intel uh, in the last few years. So they went from strained silicon, as I mentioned, in 32 nanometer node. They had enhanced high K metal gate. Then they went to the onto the FinFET. Then they had the enhanced FinFET. Then they introduced the another super FinFET. So the fin is getting taller and taller. So imagine making more than 10 billion transistors with these like huge fins, right? Uh, with very high aspect ratio, even though they are small when compared to the width, their height is actually pretty large. So you have to make the structure, put the gate around them, and a 10 billion of these transistors should work together to make sure that the chip is working. So it's just amazing. The amazing amount of engineering has gone into chips nowadays. So then they are also introducing the angstrom era. Intel is saying they have this 20 angstrom, 18 angstrom, and we don't even know like what's happening next. So these things have not been disclosed yet. These are just projections. uh, so you can imagine 20 angstrom is just 20 atoms within one transistor. You are basically controlling 20 atoms to make a device, and that device functionality should be repeatable between uh, 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 multiple transistors. Okay, so I think we have covered a good amount of materials here, and now I can go over some semiconductor fabrication techniques in detail. We fabricate the computer chips in a clean room environment. So these are special laboratories where we have hundreds of tools and equipment. Right now, the value of an Intel fab is around 10 billion US dollars. In a clean room, we have a very controlled environment. We filter all the air and make sure that there are no dust particles in the air. They are filtered through HEPA filters, which are also extremely uh, uh, expensive filters. And when you are going into the clean room, you have to wear this bunny suit. So this is me in a bunny suit just a few years ago. This was in Stanford Nano Fabrication Laboratory when I was working with some of my professors. So you have to cover your face, your hair, and make sure that none of your particles are being dispersed into the air to make sure that the microchips are completely clean, right? So because you are working with like nanometer level devices, and if you are just walking in with just these t-shirts and hair exposed, then these things can actually produce a lot of particles that can damage the chip production. Uh, so the fabrication is the process where we build circuits on the silicon wafer in a clean room. We start with 300 millimeter bare silicon wafer, and then we complete the wafer after about like a month, or it can take up to 140 days. There are multiple tools inside the clean room, and most of these things are now computerized. So there are robotic arms moving the wafers around. We do not move them by hand, and these containers can occupy up to 25 wafers each. We call it a FOOP, and the FOOP is being lifted up into this aisle, and then you can see like all the FOOPs up here. They go from one tool to another, and then to another and to another. So it's being, and once the 25 wafers arrive at a particular location, the robotic arms just take the wafer out. It processing is done by the robotic arm, and then it takes the next wafer, so on and so forth. Um, so basically, we are not touching anything. It's all computerized, but we are there to make sure that things are running smoothly. So these are the most advanced fabs, but there are also like less advanced fabs where we can move things by hand and do a lot of manual work for experimentation as well. So what are the 5 areas we have for wafer processing, right? So when you are given a wafer, uh, so Kaving and Varunika, it's 8:05. I probably need like
Uh,
another. Good
That's
five.
fine, Dr. Lakshita. Please
Yes.
continue. Yeah,
Okay.
that's fine.
Yeah. So, what are the things that we can do to the silicon wafer to make sure that we make this amazing structure, the transistor, right? So we can add certain materials, right? We can add materials by either diffusion or by chemical vapor deposition, by physical vapor deposition, PVD, or we can remove certain materials from the silicon wafer by etching, by subjecting that to chemical mechanical polishing, and then we can also create certain patterns by photolithography. Then we can change the electrical properties of the wafer, or certain other elements in it by doing some dopant implantation, right? So we can go over them very quickly. uh, the very first uh, uh, process that I'm going to introduce is the oxidation, right? So oxidation is basically introducing oxygen at a very high temperature into the silicon. So you basically put the silicon wafers into a tube, and then you have a flow of oxygen. There is an inlet, there is an outlet, and then you heat up this entire chamber. Then the silicon basically oxidizes, right? So that's called oxidation. And that could be done by either using water vapor, H2O, or just by injecting oxygen into this chamber, right? So either it could, so both actually develop silicon dioxide on silicon surface. So let's say you have silicon, this is the wafer surface, oxygen is flowing over when it is really hot, then the oxide is being formed and the oxide thickness is getting larger and larger. So the oxygen molecules come at the top, they have to diffuse through this silicon dioxide, and then they actually move on to silicon, and then they react and then form the oxide at the interface, right? So the oxide is actually formed at the interface, and the previously formed oxide keeps moving up, right? So initially, then you can imagine this oxide thickness growth is actually linear. It's increasing linearly with oxidation time because there is no oxide. But then later on, it's diffusion limited because the oxygen has to diffuse through this oxide add to the interface. So this is called the Deal-Grove model for oxidation, and I saw a few questions from this model as well in the microelectronics Olympiad. So you can look this up, and you should also read about it before you take this exam. The second process, the most important one, is the photolithography. So photolithography is used to define a particular pattern onto the chip, right? So what we actually do is the first step is to expose. Let's say you have silicon and silicon dioxide wafer, right? Now you have grown the oxide already. You apply the photoresist. It's something, it's a particular liquid, right? You apply the resist, and then you spin the wafer, and then the resist is equally coated throughout the wafer. It has a very uh, consistent thickness throughout the wafer, right? And now what you do is you expose this photoresist to ultraviolet, right, through a particular mask. We also call this a reticle, mask or a reticle, right? So this mask or the reticle has a particular shape or a pattern into it, right? And photoresist is actually made out of light sensitive materials, light sensitive chemicals, right? So when it is exposed to ultraviolet or particular other light with a particular wavelength, then it goes through a chemical reaction, and then when you put this entire thing into a chemical bath, it removes the exposed photoresist, right? Because the exposed areas have now undergone a particular chemical change, right? The other areas remain with photoresist. And now what you can do is you can put this entire thing into an etch chamber where you bombard with certain high energy ions, and then these ions would now take away whatever that it comes into contact with. It takes away some of the resist from this area, but then most importantly, it takes away some of the oxide from here, right? So then what you are left with actually is this structure, and then you can just wash away this photoresist liquid, and now you have transferred this reticle or the mask pattern onto the silicon dioxide uh, uh, interface. So photoresist is only sacrificial, right? So we only use it to transfer this mask pattern, and there could be negative photoresist or positive photoresist, and this example is only for positive photoresist. Uh, then thin film deposition, right? So this is the another method that we use to deposit materials. It's chemical by chemical vapor deposition, right? So chemical vapor deposition is basically we are using certain chemicals. We are exposing the wafer to certain gas molecules, and these gas molecules in this chamber would react with each other, and then it deposits particular films on the wafer, right? And then so it's chemically activated, right? Chemical vapor, and then they get deposited onto the wafers. Thus, we call it chemical vapor deposition. So this is also another prevalent method of depositing certain films onto silicon substrates, right? So here, if, let's say you have a particular trench and you want to fill it with an oxide, then what you do is you basically put this into the CVD chamber, and the CVD film is deposited equally everywhere with an equal thickness, and then you can also get rid of a particular. You can put this into the CMP later on, and then get rid of the CVD film at the top. So I will go over the CMP process later in the slides as well. Another way of depositing thin films is by using uh, physical vapor deposition, right? So in this technology, what we actually do is we have charged ions, we have a solid metal target. Let's say we want to deposit a particular solid metal onto the wafer. What we do is we basically take like a gun and we keep on hitting very high energy ions into this solid metal, and then the solid metal would then break off from the target, and they get sputtered onto the wafer, and by doing so we can again deposit a particular film onto the silicon wafer, right? So here there is some thinning at the bottom of a deep contact, but previously in chemical vapor deposition we get very conformal deposition. So depending on what we want, we can use different deposition techniques. uh, Removing unwanted areas or etching. So there could so etching has could be either wet etching or dry etching. Let's say you have covered a particular area with resist, and then if you put this into a chemical bath, right? That's Then it's gonna go through some wet etch. So this film is now gonna be etched using wet etch. So it's isotropic. It etches in all the directions. But dry etching is something. It's very so dry etching is actually done by putting this into another chamber that has very high energy ions or atoms, right? So these things then are very directional. They come with high energy, they hit this film, and then they keep on taking the atoms from the film, and then we remove the resist, and then we have etched particular areas of the film. So that is anisotropic. Dry etch is usually done using high energy particles, and it has a particular direction. But wet etch is usually isotropic because you are using basically chemicals, and chemicals etch in every direction once the film is exposed. um, yeah, so ion implantation is the other very important method we use to change the functionality or modulate the conductance of a semiconducting materials, right? So here what we actually do is we bombard the silicon crystal with dopant atoms. They could be boron or phosphorus, and we went over this in the first few slides. Once we bombard them, we replace the silicon lattice with this arsenic and boron atoms, and we also break down the lattice to some extent, and then the lattice is kind of crushed because we are hitting it with like really high energy atoms. So what we actually do is we anneal the crystal, and then during annealing, the crystal actually uh, recreates itself and then forms the silicon crystal, and then this arsenic, boron, and certain phosphorus other atoms also rearrange according to the silicon crystal, and they are nicely placed within the crystal. So by doing so, we can dope and introduce particular impurities into the silicon wafer. The final process I would introduce is the CMP and planarization. So CMP stands for mechanical polishing. So what actually happens is you have a particular pad, it's like sandpaper, right? So let's say you have the silicon wafer, you have some structures, now you have done some CVD or PVD deposition. So you have particular topography that are kind of like mountains on the silicon wafer. So you put it into the CMP machine, and then it's basically using some sort of a wet chemical at the interface, and it's sandpaping. It's basically has like this effect similar to a sandpaper at the interface, right? So these CMP tools are a lot more advanced than a sandpaper, obviously, and they have sensors that allows it to measure the hardness at the interface. So when you reach a particular material, the etch actually stops by itself, right? And then you have made the wafer flat again. So that's called planarization. Uh, and there are multiple CMP methods to achieve flat surfaces, and you can read up about it if you are particularly interested about CMP. So once you have made used these techniques to make the transistor, right? This is what a cross section of a chip actually looks like. So on the left hand side, you can see the cartoon. On the right hand side, you can see an actual SCM image. So this is the silicon substrate. These are the silicon fins. Let's say it's a FinFET. You can see how small it is, right? But then what actually happens is uh, on top of all these layers, you can see the metal interconnects and vias. So that's what you see here as well. You have a MOSFET here, source and drain connections. These are tungsten plugs, and then connected to that are the metal lines going into the screen, and also uh, in the other direction, right? So they are making certain connections, they are making logic gates, right? And then there are signal lines that are being routed around. So these are intermediate connections, there are global connections, and then finally there is a particular passivation layer. So here also you can see the copper interconnections that are going up to maybe up to like M11 or M12. I think there's so 10 or 12 layers in this particular chip. So to get that, you have to go through the back end of the line process. What I explained previously is the front end of the line where we actually fabricate the transistors. Once the transistors are done, we put the contact plugs, we fill this area with low K dielectrics, right? Low permittivity dielectrics, just because we don't need a lot of capacitance between these uh, interconnects, right? So if the permittivity is lower, then the capacitance between them also will be lower. And then we subject it to lithography, we etch, we do the CMP, fill with metal, many iterations go on. If you have, let's say, about 12 layers, then means it has gone through multiple iterations. And finally, we make the vias and the contacts at the top of the chip. So this is the simplified wafer process. I won't go into this. This is just a chart for you to understand. Once the wafer is cleaned, it goes through multiple processes, and then it goes back and forth between photolithography, wet uh, cleaning, and then wet etching and implantation, dry etch, back and forth. And right now, the silicon technology, I would say, has like about 400 to 500 steps to get the transistors uh, uh, onto the silicon wafer. So this is a very simplified process flow for an NFET fabrication. I just want to make sure that I go over this because we discussed some of this uh, processes just now. We start with the silicon substrate, clean it with some oxide, some silicon with Piranha solution, sulfuric and peroxides. Then we do the wet oxidation to make a thick oxide, and then we do the photoresist coating, litho and exposure to make this particular structure. Then we do the wet etching to make sure that this area is etched in the oxide, right? And then we do the oxidation again, oxide forms on top of the layer. Now we do the chemical vapor deposition of polysilicon gate. Next we do the litho and then the contact etch. Then we do the ion implantation, right? Phosphorus ion implantation. So that means these are going to be N wells, N type wells, and then we anneal it to make sure that the that the silicon crystal is now back to its original state. And then again we can grow some oxide, do the etching, put the tungsten plugs, and then the CMP, and then you have a transistor on the silicon substrate, right? So this is a really simplified process flow for long channel MOSFETs. For nowadays, as I mentioned, it goes through a lot and a lot more processes. So I could only find one exam paper from 2016 about microelectronics. So I could see that in section 4, they have asked certain questions about semiconductor processing and electronic devices. So these are the topics that I thought were relevant for you. They have asked questions on minority majority carriers, Fermi direct distribution, band gap. Then they have also asked certain questions on PN junction diodes, depletion width, Galon diode, Schottky diode, certain other variations of the diodes. Then the transistor, definitely you should see the MOS capacitor. I did not even cover that in this lecture. Uh, then MOSFET transistor, short channel effects, device characterization, and IV curves and threshold voltage, and so on and so forth in this section. So I also found a few MCQs that are actually relevant from what we just covered in this presentation. One question is the basic MOS capacitor in a MOSFET device is actually made from what? Can someone answer if you have been listening to the lecture? So it should be the gate, oxide insulator, and the semiconductor, right? MOS capacitor is metal oxide semiconductor, right? And then what are majority carriers in N-type semiconductors? Majority carriers are going to be electrons. And what domains does a semiconductor diode consist of? It has P and N, right? Electron drift current density is given by this equation, right? Where mu n is defined as, right? So n is the concentration of electrons or holes in a particular semiconductor, and mu is the electron mobility. So when you multiply them, what you actually get is the drift velocity, we call it. Okay. Uh, an NMOS transistor starts to conduct when VGS is greater than VT, right? So the potential difference between gate and the source terminal is higher than the threshold voltage. So the answer should be B. And in section 5, I could also see that they have covered certain areas about silicon wafer, the crystalline planes, silicon dioxide wet and dry oxidation processes, lithography, doping methods, and the deposition methods. So I also found a few questions that are relevant here. The oxide layer of a MOS transistor is formed by the following method. It's done using thermal oxidation, right? So MOS transistor oxide is made using thermal oxidation. So is it dry oxide or a wet oxide? It's most probably a dry oxide where we just use oxygen, because dry oxide is actually of higher quality, and we need very high quality oxide for the gate of the transistor. Okay. And then what is the technology roadmap of photolithography process? Coating, then comes the alignment, right? Then we expose it through the reticle, then we develop it, right? Chemical development to get rid of the exposed resist, and then we do the etching. So this is the answer, right? Uh, so the signal propagation delay in IC is mostly determined by, actually they are determined by a whole lot of things, but mostly the delay comes from the interconnect nowadays. Okay, as compared to the diffusion process, the ion implantation is realized at, right? So for diffusion, you need a higher temperature to diffuse the material into the silicon wafer. But ion implantation already has really high energy in its in the atoms already, so you can do it at a lower temperature, right? In the IC manufacturing process, the chemical mechanical polish in CMP is used to It can be used to reduce the thickness of the substrate, for chemical activation, or for planarization, or to form vias. So it's either C or E where all the answers are correct. So I believe it's E. I'm not exactly sure what they're looking for here. The speed of silicon thermal oxidation is limited by uh, the speed that the gas can actually diffuse through the silicon dioxide into the silicon surface, right? So the speed of diffusion oxidants through the silicon dioxide layer to silicon dioxide interface. So there are also certain essay questions in this exam, and for that you really need to know the theories, right? So I highly recommend you to go over certain chapters. I think I mentioned two books in this presentation. I can also share the slides if you think that's going to be helpful for you in PDF format. And then with that, I would like to thank you for your attention and also for your time. And if you have any questions, I would like to take the questions. Thank you.